This part of assignment 147 is going to introduce a very important principle in chemistry called Le Chatelier's principle. Le Chatelier was a French chemist. You can see his picture here. And you can see the dates. So he's spanning the turn of the 20th century. His principle is published in 1884. So the principle, it's originally written in French, but fairly well translated here. If a chemical system in equilibrium is subjected to altered conditions, a new equilibrium will be established. The shift in equilibrium opposes the introduced perturbation or alteration and acts to moderate these changes. So these are the important verbs here. The shift will oppose the change and moderate it so that what might have been a big change becomes less of a big change. I'll try to demonstrate that here with these graduated cylinders. This is a system that can be used to demonstrate shifting equilibrium. So I have here two cylinders. They're both filled with water. They have a pH indicator dye which makes them different colors. So this is acidic and this is basic. They're connected by this plastic tube here, which would allow molecules to flow from one cylinder to the other. At this moment, although you can't tell, molecules are diffusing through the tube. For every one that goes from left to right, a molecule goes from right to left, and that's what creates this equilibrium, the two arrows. So you saw the first example. So if you have color, use color. If you don't, it's okay. But we had the blue cylinder here. And we had the yellow cylinder on the other side. The original situation has an equilibrium. And I'll represent that with a couple of arrows. We have molecules going from left to right and molecules going from right to left. At equilibrium, we have equal number of molecules moving. So the number of molecules going right to left, which would be from the blue to the yellow, is equal to, that's the key for equilibrium, number of molecules going left to right. So here in my diagram we have equal arrows going right to left and left to right. If you relate this to what Ms. Holtz was presenting, if we have a weak acid, for example, I'll use this one. This is formic acid. In an aqueous solution, it certainly dissociates. The H plus here, the polar H plus, the polar hydrogen, can dissociate. The non-polar hydrogen does not dissociate. And this can be an equilibrium. And if it is at equilibrium, which is naturally established, then for every molecule here that dissociates, there will be a pair of these ions that reassociate. So dissociation, left to right, is balanced by reassociation, right to left. Equilibrium is naturally established in any weak acid solution. So here, perhaps you imagine the blue being these dissociated ions and the yellow being the weak acid molecules themselves. So now I'm going to disrupt the equilibrium. I'm going to add some additional blue to this side. You should be able to see the additional blue is now dropping.
Adding more blue disrupted the equilibrium, but this is going to restore an equilibrium by shifting molecules from the side that has too many to the side that has not enough. This is a natural process. The restoration of equilibrium is completely automatic. And this is what Le Chatelier's principle is all about. If you disrupt the equilibrium, nature will find a way to fix that. So at this point, equilibrium has been restored. The levels are equal on both sides, so there's no pressure essentially to cause molecules to go one way more than the other. So now, once again, for every molecule that goes from right to left, a molecule goes from left to right. Equilibrium is restored.
Here on scenario 2, you can see I've drawn a picture that illustrates what we did. Added extra blue, so make your sketch appropriate for this scenario. And here's where extra blue was added. And this disrupts the equilibrium. So we can write the words here. Extra blue molecules added. Disrupts the equilibrium. So this is what is meant in Le Chatelier's principle by a stress or perturbation or a change. We've disrupted the equilibrium. At this time, with the extra blue, then we have a bigger arrow going from right to left, and a normal size arrow going from left to right. So here is an imbalance, right? An imbalance. To restore the equilibrium, molecules shift. So in this case, blue molecules transform into yellow. So this decreases the extra blue, decreases the extra blue. So if you add extra, then the equilibrium shifts to remove the extra. So the shift would be, if you add extra, take some away, take some away. Now in chemistry you can't just destroy the atoms that were added. They can only be removed really by shifting to the other side of this chemical equation. So this is called a shift to the left. Equilibrium shifts left in my picture. If we go back to an example, let's say we had a nice equilibrium here with a weak acid. But then we dumped in a bunch of extra H+, dumped in some strong acids. I'm drawing this very large, and that signifies extra H+ added. Then that would disrupt the equilibrium, and in order to restore the equilibrium, the reaction would shift in this direction, and some of the extra H+ that was added will turn into HX. This should remind you of the equilibrium island where the boat of lonely single men lands on the island, and that will increase the number of couples as the lonely men, the extra lonely men, pair up with some of the single women that are present. That's what's happening here in Le Chatelier's principle. To summarize, the stress is the extra blue added. The shift reduces the extra blue by having a bigger arrow going this direction. And this is what is meant when Le Chatelier says, subject to altered conditions, a new equilibrium will be established. You saw that in the video. The shift in equilibrium opposes the introduced alteration and acts to moderate. So extra blue, opposing that is get rid of the blue. Moderate, there was a whole bunch of extra blue. In the end, there isn't that much extra. The equilibrium shifts to moderate this change.
A different way to disrupt the equilibrium would be to subtract something. Instead of adding, you could subtract from one side or the other. In this case, I can do that with a vacuum pump. So I have a vacuum here, and I'll pull out some of this blue, and we'll see that that disrupts the equilibrium, but then nature will restore that equilibrium. So you can see I've taken out quite a bit of the blue, but now the yellow is dropping and turning into the blue. It's trying to restore what was taken away. That is the way it will once again establish equilibrium, is by replacing what was lost. And this is another part of Le Chatelier's principle. If you take something out of the equilibrium system, nature will restore what was lost. So once again, you can see balance is restored. We're at equilibrium once more.
Scenario 3, you see I've sketched the colored cylinders here, so you probably want to do that first. In this one, the change was we removed some of the blue. And that, again, disrupted the equilibrium. So I'm going to word it this way. When some blue molecules are removed, so I'm using a metaphor here, it creates a hole, right? It's a deficiency. So I'll put that in quotes. It doesn't really create a hole, but it does create a deficiency in those molecules that nature will fill. And it does this to decrease the potential energy, that original all-encompassing rule. Nature fills by shifting the equilibrium to create additional blue. So this is a shift in equilibrium to the right. We can illustrate that with arrows. So now the arrow pointing from left to right is bigger than the arrow pointing from right to left. By removing the blue, we essentially made it unlikely for molecules to go from right to left, and therefore the net shift will be to the right. So I can write that in words here. Equilibrium shifts to the right. Maybe I should add some words there, huh? To restore. To restore what was lost. So this is another example of Le Chatelier's principle. If the stress or the perturbation is to say we've lost something, then the way to moderate that change is to recreate what was lost, to replenish what was lost. That's Le Chatelier. Here's a specific example. I can again use a weak acid. These principles are general and therefore apply to any sort of equilibrium. So now let's imagine instead of the normal amount of H plus, we just have a really tiny amount of H plus, because perhaps you added a base. That shark gobbled up all these H pluses. There are very few left. So in such a situation as this, the equilibrium will shift to restore what was lost. Restore what was lost. So this arrow going to the right will be big, and the arrow going to the left will be tiny. That should make sense to you. If there's very little H plus, then the rate at which X minus and H plus associate, the rate at which they find each other and bond, will be very small, and therefore this tiny arrow on the bottom is realistic. So this, but if let me write it this way, if H plus is removed, or decreased I should say, comma, equilibrium shifts by dissociating additional Hx, sorry this doesn't fit in the box, to restore the missing H plus, exclamation point. Alright, that's Le Chatelier.
A common misconception among students is that equilibrium means equal quantities on both sides of the equation, for example. And that's not true. I can shift this equilibrium now by changing the relative energies of the two sides. So perhaps I will lower this down. So now the blue side is at a lower potential energy than the yellow. And when this happens with molecules, then the equilibrium will favor the side of lower potential energy. So you can see right now that yellow is dropping, blue is rising, and we'll end up with an equilibrium in which the two sides do not have equal volumes or equal number of molecules. So you can see this is up around 400 milliliters, this is down around 300 milliliters. This is an equilibrium, even though the two sides do not have equal number of molecules.